Okay, welcome. In this lesson, we are going to see the famous average return volatility graph, in which we'll at the beginning put just some world indexes to see how they behaved in the last decade. So to see which one are the most risky ones, which one are the less risky ones, which one are the most profitable ones. Not always the most profitable are also the most risky. And then we will build the famous efficient frontier for a set of portfolios. So the famous curve that every student of economics sees. Okay, let's start to import the usual stuff. The tickers. These are some tickers of international stock indexes. Some of them are well known, other are mysterious. Okay, imported everything. So let's take the last 10 years of prices. We will have a lot of misses here because it happens that a market is open and a market in another country is closed. So, can you see, for example, here some missing. Okay, however, a lot of stuff. Okay, now we calculate a simple return, SR. I use abbreviation because I'm tired. Prices, PCT change 1. SR. Okay, first line is always missing. Okay, fine. Simple return mean. Okay, and the standard deviation. So how to use these two data, put them into a data structure to build a scatter plot of expected return on the horizontal axis and volatility volatility on the horizontal axis and expected return on the vertical axis. This is the classical return volatility graph. So you could put them by hand, but in the big data course you won't do it. Okay, first of all, if you don't mind, I will convert them to annual rates because if you see daily returns, it's difficult to distinguish them. Okay, so how do we convert a daily return to an annual simple return? Or better, it's the annual average simple return. Okay, it's a simple return mean multiplied by 250. No, 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 because this is a simple return. You do this for log return, but this is a simple return. So you have plus 1 to the power of 250 minus 1 AASR. Okay, now these are yearly returns. So annual average simple return. And here the annual volatility, it's it's a simple return standard deviation. Okay, here instead you could just simply multiply by 250. Well, we could also leave it like that, but multiplying by something just makes it a little larger and easier to see. However, if it were the variance, you would multiply it by 250. Since it's the standard deviation, you multiply it by the square root of 250. Okay, I tell you, for a graph, it doesn't make any difference because you multiply all the values. So, okay, just to take a look at it. Okay, so some are more risky than others. Okay, now that we have these two data, we put them into an appropriate data frame. In this way, table equal PD data frame. Okay. The syntax to build a new data frame starting from two different data series, is the following. So you want to put the two series. Okay. Well, we could build it simply passing AASR and then passing AV, but I want also to have the headers and everything. So open graph parenthesis, average annual returns, colon AASR, comma, e volatility, colon, AV. Okay. Okay, here you put what will be the the row indexes, which in this case will be the tickers. Okay. I hope that they are in order, because I'm afraid that the tickers, my ticker list, can you see? It's not in the same order. This could be a problem. So instead of tickers, I pass AV or AASR dot index. This way it's in order automatically. Let's see. Table. Let's check this one. AXJO 60042. Yes. Okay. So I fix it also in my notes, because this is a big issue. Okay, very well. Now that I have this table, I can plot it. So table dot plot. This time I will build a scatter plot, kind equal scatter. Let's see how does it look like. Requires x and y column. Oops. So x equal volatility, comma, so this one, and y equal average annual returns. Hop, another problem. Volatility, the capital V. Okay, scatter plot. Let's make it a little larger. Comma, fig size equal 2010. 1510 is enough, perhaps. Okay, font size equal 18 and S equal 200. This is the font of these numbers, and the S is how large is the symbol. Okay. If you want the symbol to be smaller, you can just 100. Okay. Also the font is a little exaggerated. 14. Okay, very well. Also, I didn't discover how to increase this font here instead. Okay, so you can see the indexes. However, unfortunately, I don't know who is who. Can you see? Okay, in order to get who is who, I go here. You have to plot a table. Before, you have to import matplotlib as MP. It's a library which contains things to plot. Okay. Now, for I in table index, I have to go through all the elements of the table index and pyplot dot annotate. So there is the pyplot annotate, okay, which lets you annotate the graph. Okay, I xy. It's a little technical, but okay, I will copy, and perhaps it's better if I leave it unmatched parentheses. No, it's not return, but it's average annual return. Okay. There is a little overlapping here. Can I decrease the font to a 12? We have less overlap. Still a lot of overlapping. However, you can see that IXIC is the one which has the best return. What is IXIC? IXIC ticker. Nasdaq. Okay. Okay, what is this one? The most risky one. JNOU. And JN0U. JN0U. Okay, but Johannesburg. The most risky one, even though it doesn't. You can clearly see some things, for example, that given the Nasdaq is here, all the things which are below and on the right are not good because they have more volatility with less return. So given that the Dow Jones is here, all the things which are below and to the right are not good. Given that here, this one perhaps it could be the Taiwan index, all the things which are below and on the right are not good because they have less average annual return and more volatility. This one is instead good because even though it has a very low return, but at least it has a very low volatility. IPSA, what is IPSA? IPSA, IPSA. Can I get also? Okay, IPSA exists, but mystery. It's a mystery ticket. Santiago. Santiago, very few volatility. Very well. Okay, and now let's go to the efficient frontier. Oh, sorry. Okay. For the efficient frontier, we need instead some stocks. We'll build a portfolio. So I take the stocks here. We'll build a portfolio. I just copy and paste. So okay. So the usual prices. Okay, I don't even take a look. I'm pretty sure that we get them correctly. Simple returns. Prices. I copy from above. I'm lazy. Instead of copying from above, if you are particularly lazy, you just execute from here. You see? Okay, so I'm particularly lazy. Okay, so I execute from here, I get a simple return. Then I have to remember, perhaps it's better to copy, because if I rerun everything, I will forget to get it, and I will stay here 3 hours wondering why it doesn't work. Okay. Now, SR min equal SR dot min, SR std equal SR dot std, and SR cov equal SR dot cov. I remind you that in order to get the risk and the return of a portfolio, you don't need to calculate the returns of the portfolio. It's something we have seen in a previous lesson. You just need the average return and the covariance matrix. You don't even need the standard deviation, so let's remove it. Okay, we just need these two information. You can get the return of your portfolio, given the weights clearly, and the covariance. And the risk. Okay, now I want to build 1,000 different portfolios, and then I would like to plot the graph here for the 1,000 different portfolio to show you that the distribution is exactly the one forecasted by the theory. Okay, I want to build them randomly. So I have to build the weights randomly. So I take random numbers from 0 to 1. Okay, the weights of each. How many? We have 6 elements in our portfolio and 1,000 simulations. So I have 1,000 simulation for 6 elements in my portfolio. Okay, what's the problem here? 1, 2, 3, 4, 5, 6. Okay, beware because it's in column. So the first portfolio is this one, this one, this one, this one, this one, this one. What's the problem here? The problem is that the sum is not 1. You can easily see 0.94, 0.75, the sum is not 1. So you have to rescale them. Okay. So, I have to weights equal weights divided by the sum of weights. Sum of weights give me the sum in the vertical direction. I'm not sure, so let me check. Yes, it's a sum in the vertical direction. In fact, this one plus 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 this one makes 2.9. Okay, so very well. Now, if you divide by the sum of weights, you have, and you see, always the sum of equal to 1. Very well. Okay, now a portfolios, no, PR, which stands for portfolio random, equal numpy, portfolios returns let's write it because portfolio returns equal numpy dot weights dot sr mean. Okay. I remind you the formula. You just multiply the weights by all the returns, and you get the portfolio return. Let's see whether it works. No, there is a problem of dimension because this one is 6 by 1000 and this one 6, so I just use the trick of transposing it. Now it's 1000 by 6, so I completely reverse it. Okay, and let's see the portfolio returns. Okay, so these are the return of my portfolio. It's an array with 1000 elements. So we have all the possible returns. Now we have to get the volatility. So portfolio volatility equal numpy dot. I remind you the formula. It's weight numpy dot of weights, numpy dot of the covariance matrix by the weights. So weights, comma, numpy dot of SR cov weights. Okay, it should work. Okay, let's see whether it works. Again, the problem is that this is SR curve. Let me show it. SR curve is 6 by 6. Weights is 6 by 1000. So the result here is 6 by 1000. This is 6 by 1000. No, okay. Okay, in fact, 6 by 1000, 6 by 1000. So I have to transpose this one again. Okay, let's see. Okay. No, I should get... the problem is that I get a matrix, but I should instead get a... Let me see. I get a matrix, but I should instead get an array like this one. Okay, where is the problem? Okay, this is 6 by 6. This is 6 by 1000. Okay, the result is 6 by 1000. This is again 6 by 1000. And I want it to be... I have to transpose this one, perhaps. No, because I get 6 by 6. I have to get 1000 elements. No, it doesn't work. Okay. This one doesn't seem to work, so there is no way out. I'm very sorry. You have to do it step by step with a loop. You have to do it step by step with a loop. So first of all, we built a table where we have to put everything. Table equal pd data frame. I build an empty table. Columns equal return and volatility. Okay. Now for I in range 0,000. Okay. I build portfolio return equal, and this one works. In which I use only one of the weights. So this means the entire row and only the ith column. So at the beginning will be the column 0, column 1, column 2, column 3, column 4. Okay. And portfolio volatility equal, and here something similar, but here SR curve and another numpy dot of weights of column I. Okay, this should work. Let's see, I'm not sure. And now we put in table, we insert in the table a new row made up of PR PV. Sorry, lock of I equal PR PV. Okay, I insert the table a new row made up of PR PV. Let's see if it works. It's stuck. No, it seems to work. Bah, seems to work. Okay, there is the only little problem is that the return should be annualized. So plus 1 to the power of 250 minus 1, and I have to put the parentheses. And this one, we multiply it by numpy.sqrt of 250. Okay. Oh, and finally, I could have done it also after. The plot of the table, I am lazy, so I copy from above. I copy also. I don't. This time we don't need to know which portfolio is which. X uguale volatility, return. Okay, you for sure recognize the standard graph of the efficient frontier. Okay, well, this is the efficient frontier, and these are the optimal portfolios. If you wish, you could write for each one little which are the parameters, so you get to know which one is which. So starting from here, this is the one with the lowest volatility, and the lower, and not the lowest return, but among the best one, the one with the lowest return. These are all the best ones. This is the one with the highest, not the one with the highest volatility, actually, the one with the highest return. And this one is suboptimal because there is this one with a much higher return and less volatility. Okay, the efficient frontier, Markowitz efficient frontier. And now one last topic. Sometimes you wish to make a heat map of the correlation. So you wish to print the correlation matrix with a heat map to see how strong your tickers, your stocks are correlated. So we take prices.core. Okay, this is the correlation matrix. However, imagine that if you have a big one. Okay, let's take the prices of the indexes. So a big one. Okay. So I take the prices. I take also the logret. Where is the prices per it's not the logret, the returns. Okay, now I have the simple returns of the indexes. Sorry. I have already spoiled to you what I'm going to do. Simple return. Okay, this is the correlation matrix. Well, it's impossible to look inside. It's a nightmare. Okay, so we wish to draw a heat map. Let's see what is it. Before you have to import Seaborn. Don't ask me why the name. Okay. MP, which is matplotlib, .pyplot, which is Python plot, .figure fig size equal 2010. Unfortunately, Seaborn uses a slightly different way to set the fig size. And now Seaborn dot heatmap. Okay. sr.core, so we'll draw the heatmap of the correlation. Cmap equal reds, written reds, it means that you will painted red, are not equal true, v min equal 0, v max. I will explain in detail this are not kys equal size 8. Okay, up. And the result is wait, because the computer has to do a lot of calculation, has to draw a lot of things. Come on. Yeah, okay, wait, but not too much. In the meantime, I enlarge it. Here it is. Okay, this is called heat map. So you can see, first of all, reds, because it's red. If you choose, you can choose greens, blues, grays. Yellows doesn't work instead. I never tried oranges. You can see the ones, but obviously the diagonal is all full of ones, but you can immediately spot that it's pointless to put A, X, Y, O and A, O, or D in the same portfolio. It's also pointless to put GSPC and Dow Jones. Okay, while this one, very low correlation, which is between KLSE and the root, they should be put in the same portfolio. So you can immediately spot it. Vmin is the minimum value. I set it to 0. I could set to 0.1. Vmax is the maximum value. Okay. Well, it is a correlation, so a not true means that there is the number. Okay, it is the size of the number. Well, this is a big matrix, so I put a small size. Usually I put 12 or 14. Okay, and as I told you, instead of red, let's see whether oranges works. Yeah, it works also oranges. It works also with blue. Grays is the most elegant one. Oh, wonderful. Okay, and you can enjoy yourself doing these pictures. Bye bye.